Hi guys, here's another sample from section 1.2's homework assignment online. If we put 7 into this equation, it'll be 21 minus 21, and the absolute value of 0 is 0. We put a 7 down here in the bottom, and 7 minus 7 is also 0. That means we need to factor cancel and shove it back in. You could also graph them. Sometimes the graphs will give you a close estimate of what it is, and sometimes the graphs will give you an exact estimate, an exact value of what it is. So the graph of this one, as we plug in numbers that are intimately close to 7, but from the left-hand side, like 6 and 5 and 4 and 6.9999, when we plug in a 6, we're going to get negative 3, and the absolute value of negative 3 is 3 over 1. When we plug in a 5, we get 15 minus 21, which is negative 6. Negative 6 divided by 2. Negative 6 is absolute value divided by 2. 3 again. So we get a series of a bunch of 3s. When we plug in 7, it's a whole. It looks like this. When we plug numbers in that are bigger than 7 or coming from the right-hand side, the absolute value bars don't do anything. They don't have any impact on a number like plug in 8. 24 minus 21 is 3, and the absolute value of 3 doesn't change it. When you plug in 8 down below, that is negative. So 3 divided by negative 1 puts us down here, and you can plot some more points if you want, but that's what it looks like. At 7, it's discontinuous, and we're going to talk about discontinuity next week, but this one has jump discontinuity. So as we hone in on this limit, but from this side, it's 3. As we hone in the limit, but from this side, it's negative 3 down here. So as we hone in on this limit, hone in on 7 bidirectionally, since these two values aren't the same, then this doesn't have a limit. That's the graphical approach. Now let's take a look at the algebraic approach for this problem. Algebraically, if you know you're plugging in numbers that are smaller than 7, you know that this absolute value on the top has to do some work. So, rewriting it in piecewise form without the absolute values, it would look like this. The opposite of 3x minus 21. Does that make sense, everybody? All over 7 minus x. So again, when we know we're going to plug in numbers that are approaching 7, but from the left-hand side, we know they're going to be numbers less than 7. And when you use numbers less than 7, like 6 or 5, you create a negative number up here where the absolute value does work. Negate that known negative number because that's what the absolute value bars do. Distribute that negative number through, and you get negative 3x plus 21. And then factor out a 3. Sorry, so sloppy. When you factor out a 3, you get negative x plus 7. All over that denominator that's 7 minus x. The 7's positive, the x is negative. These things cancel, and you're left with 3. The algebraic approach for numbers that are coming from the other side of 7 or bigger than 7. When you plug numbers in that are bigger than 7, this number here will be positive, and the absolute value bars are inconsequential. So they're not even needed for that. Divided by 7 minus x. This time, to get the 7 to be positive over here on the back side, I'm going to factor out a negative 3. So when you factor out a negative 3, and write down what's left after you factor out a negative 3. Factoring a negative 3 out of there, because when you redistribute, you'll get the positive 3x. Factoring a negative 3 out of there, the x are negative and the 7s are positive, and so these things cancel, and you're left with negative 3. So we have two different approaches for this, the geometric approach or graphical approach, or in this case, the algebraic approach. When the limits as you approach it from the left and the right do not match, then the limit as we approach it bidirectionally is always undefined. I hope that helps, guys. We will see you in class the next A day.